So hello, we're going to be doing a simple antenna comparison, a relative comparison today. What I have here is an antenna which is built into, where's the box? Built into a device which goes on top of lampposts. It's a lamppost control system. It uses a technology called WiMAC at a frequency of 869 or thereabouts megahertz. The antenna here is actually designed for 869 megahertz. It's actually got that 869 written on it here. You probably can't quite see that in this lighting. And this is a quarter wave vertical antenna at that frequency. It's a ground plane antenna. This is a ground here. What I've done is I've disconnected it from the transmitter and receiver on the circuit board here, and I've attached this cable to it so I can plug it into my test kit here. We're going to compare this antenna to a simple vertical dipole here, which is made from a piece of old Wi-Fi aerial. All I've done is extended the antenna here and at the bottom to make it into a quarter wave dipole. It's actually, really, the correct term is a half wave dipole, but the top side and bottom side is 1/4 wavelength, and so it's half wavelength in total. On the receiver, we're going to use this antenna here, which is a quarter wave ground plane antenna, again tuned for roughly 869 megahertz. To transmit, we need to make a simple carrier wave at 869 megahertz, and the way I'm going to do that is using this device here. This is a Lime software-defined radio. This goes from about 100 kilohertz to I think just below 6 gigahertz, and inside we have the RTL-SDR circuit board. Connected to the antenna ports on the board are these sockets here, just to make life easier and so I don't short out the board and break it while I'm using it for some experiments. And we're just plugging in one of the connectors here, which is the transmit array 1 from the first transmitter, to a bit of cable, and that cable will go to our test antennas one by one so we can compare the relative gain of the antennas. To receive the signal, we're using an RTL-SDR, another software-defined radio, and this will be tuned just to 869 megahertz. And we'll see a trace on a spectrum analyzer, which will give us the signal strength of the received signal at the receiver. So it's quite a simple comparison. It's not an absolute comparison. I haven't got an anechoic chamber and the expensive test kit to test this to that kind of level. But what we're going to do, what we really want to find out is this a high gain antenna? Does it have any more gain than a bit of wire? But to make life a bit more interesting, what I've done is I've made a different antenna, which actually is a high gain antenna, and that antenna is this antenna here. This is made from an old cooking pot at the back here, which happened to be exactly the right diameter, which is pretty handy. But we need it to be slightly longer than the cooking pot here, so I just put some cardboard on around here, and on the cardboard is some silver foil. So what we have here is the antenna input socket here, which goes in just about half wavelength from the back, and then there's about, was it roughly a wavelength or so? 1, 2, 3, yeah. From the antenna to the front, from the input socket here to the front of the antenna. And inside, just at the back there, you can see is a little antenna here. That's the vertical. It's exactly the same as this, really, and the same as this antenna here, but it's stuck inside this can. And the idea of the can is it focuses the signal of the RF coming from the antenna. It bounces off the back and it focuses it down this path here. So you get some relative gain over this antenna here. And I reckon it might be about 6 or 7 dB gain over this antenna here. But we'll find out soon. We'll do some measurements and work out what the gain is. So this is the transmitter we're using. It's a RTL-SDR software-defined radio, which I put into a little box just to protect it. That's inside there. And the RTL-SDR is linked up to various antenna ports here for transmit and receive, and then via this USB 3 connection to a Linux laptop. And we're using GNU radio, and we've strung together some GNU radio modules that cause it just to transmit a simple, quite narrow band carrier at 8 869 megahertz. And that comes out of the antenna port here and through the cable out to that external port and into our antenna. It's currently still connected to the antenna here, the big silver abomination, but it's quite interesting just to show that you can make antennas really simply with bits you find lying around. This is the dipole we used earlier is just a bit of old Wi-Fi antenna which I've chopped off, and I added some bits of cable to make it the right length for a quarter wave dipole at 869 megahertz, and that's compared here to the antenna we have on test, which is the antenna from Harvard Electronics, for one that we've seen on some other videos. And this even has a, oh look, it's got a little blob of resin there, you can just see sort of shining in the light. And of course it's got the blob of resin at the end there, which you can just about see there at the end. So that's it, we've compared the original antenna here, and we've compared that one to a simple quarter wave dipole, and we compared those two antennas to this thing here, which I made out of bits of tat, and we found that the Harvard quarter wave vertical antenna and the quarter wave dipole are pretty much identical in gain, and then we have the antenna here, which is about 6 dB greater gain than those other antennas. Now, before we actually test the antennas, what I want to do is do a wired-in test. So what we're going to do is plug our receiver into this receiver laptop here. There we go. And the transmitter we plugged into this laptop here, like so. And what we'll do is we'll connect the transmitter directly to the receiver. But there's relatively high signal coming out here. It's not massive, it's maybe sort of 5 milliwatts or so. We don't want to put the 5 milliwatts directly into the receiver because it will probably damage your receiver. So what we're going to do is put some attenuation in line. And I have here two attenuators. This is minus 5 dB. This is minus 20 dB. So we have a total of 25 decibel of attenuation here. And what I'm going to do is plug that into here, to our receiver, and then we're going to cable from the transmitter, so our transmit port here, into the receiver. If I can get it plugged in. Oh, that's the wrong side. So we have a direct connection now from the transmit to the receiver, and we'll see what kind of signal we got on the receive when it's plugged in directly. So I will start that receiver there. There we are, so currently we're getting no signal at all, absolutely nothing whatsoever. I go back to our transmitter. I'll have to restart it because I unplugged the SDR, so I'll just restart that. There we are. Now, okay, so I'll start the transmit now. And there we are, so we've got a good signal here. Let's measure our signal. And it's neg 14, so I'll take a screenshot of that for later. And I'll be taking screenshots throughout the experiment just so we can capture these images from the spectrum analyzer. And I'll save that, and I'll just call it wired, W-I-R-E-D, there we are. That's saved there. There we go, okay. So let's now plug some antennas in and see if we can measure the gain of our antennas. And just to give you an end-to-end view, this is the transmitter side here, and the receiver is, let's pan around here, through that doorway, and just there, you can just about see the antenna there, that's the receiver there. I'm not sure how far away it is, maybe about 15-20 meters away. and the receiver has been put inside that doorway, because if I had both inside this large basement room here, there'd be all sorts of reflections and it'd be hard to get a accurate reading. And I didn't want to do it outside because it's raining and I don't want to get wet. So that's our end-to-end test setup. So here we have the transmitter, which is the original Harvard electronics lamppost device. It goes on top of the lampposts. The electronics have been removed and I've attached a cable to the antenna, and that cable is attached to a RTL-SDR, which is in transmit mode using GNU radio, and it's transmitting a carrier, just a single carrier, at 869 megahertz. The output is very low power because all we're going to do is compare this antenna to another antenna, which is a simple dipole, this one here, and we'll see if this is in fact a high gain antenna compared to this simple dipole, which I made out of some bits of wire. This here is the receive antenna. The receive antenna is a simple quarter wave ground plane vertical, and it is connected to a laptop here, and the laptop is using an RTL-SDR receiver, and as you can see we currently have a signal there at 869 megahertz, and the peak is neg 45-ish with quite a high noise floor. But you see the peak there, that is a signal coming from the transmitter linked up to that original Harvard electronics antenna. So now we're going to change the antenna here. We'll take off the Harvard antenna and instead put on this simple quarter wave dipole here into that same socket, and we'll go and see in a minute how our received signal is in comparison to the original Harvard antenna. In about the same place. There we go. And we'll start the transmit and we'll go and see what the received signal is like. So here we are now back at the receiver, and we have a signal being received on 869 megahertz. It's about neg 42.6, neg 43-ish dB, so it's actually a stronger signal using my little dipole antenna than it is using the original Harvard antenna, which is quite funny. So my little homemade bit of tat made from an old Wi-Fi aerial is actually transmitting a better signal. It's higher gain than the original Harvard engineering antenna, which is built into that device. That's mildly amusing, but that's the way things go, isn't it, sometimes? So there we go, neg 42, say neg 43 dB there. So this is the next antenna we'll try. This is an actual moderately high gain directional antenna. It's actually a cantenna, the same kind of thing you'd build for Wi-Fi using a Pringles scan. Only this cantenna is made from a cooking pot, which happened to be the right diameter, and I've extended it with some cardboard covered in some silver foil. Inside the antenna we have a quarter wave monopole here, connected to a connector at the bottom, and that connector then connects to the transmitter, which you can see just there. And it's the same antenna port as the other two antennas. So let's start the transmit and go over to our receiver and see what the received signal is. So here we are at the receiver again. So our transmitter is now transmitting using our cantenna, made from an old cooking pot and some silver foil. And we can see now that the received signal strength has gone up. So now we are at neg 38.3. I think we're about neg 34. So that means we've gained about 6 dB over those other antennas. So the actual high gain antenna gives us about 6 dB over the dipole and the vertical. They are about 2 dBi, so 2 dB gain over an isotropic antenna. So that means we get about 8 dB gain using our cantenna, which is about what you'd expect from such an antenna system. So that's working quite well.